All right, folks, for the last video, we'll jump into some practice problems. There's just two here. We'll probably do more in class, so we'll start off with some conservation of momentum. When you read a problem and decide that it's conservation of momentum, you generally want to decide what type of interaction it is. And this one is an explosion. So there's a spring between the two carts that pushes them apart. Now, if it looks like you're solving for mass or velocity or something like that, you would want to set up an equation for conservation of momentum. When we go over some maybe of the AP Classroom multiple choice questions, we won't necessarily need to set up an equation like that, and we'll talk about some different strategies for that. But we're just going to set up the general equation for an explosion. So they start together, they have a common initial velocity, and then they are pushed apart by an internal force. So that's our initial situation. We get some important information from the problem. The first one is m2 is equal to 3 times m1. So I'm going to just use m. I'm going to say that m1 is m, and m2 is therefore going to be 3m. So every time I encounter m2, I'm going to replace it with 3m. They are stuck together, moving with a speed of positive v. And then m1, after that explosion, has a velocity of negative 2v. And then m2, missed the 2 there, is we are looking for the final velocity of that. So it can be like a little overwhelming in these problems to just look at everything and decide, well, what is the variable that I'm solving for? Just keep in mind we're solving for the new velocity of m2, and that's going to be the v2f that I have there. So now I want to simplify everything. This is a fairly common setup for conservation of momentum, where you have relative masses, because the mass will eventually cancel if you do it that way. So on the left-hand side, we have 4 times mv. On the right-hand side, this term is negative 2mv, and this term is 3m v2f. So now I can work on solving. Again, I'm solving for this velocity way over here, so what I am going to do is I'm going to add 2mv to both sides, and that's going to make it 6mv equals 3m v2f. That gives me now a good opportunity to cancel m. I could have done that really at any time. And I just divide by 2. Divide by 3. So it's 6v divided by 3. And that's going to give me my final velocity, and so that's going to be positive 2v is going to be that final velocity. And so in this situation, they are pushed apart, and even though they're different masses, they end up traveling at the same speed. That might be a little misleading. If you look at the initial velocity, we talked a little bit about how you can predict changes in velocity based on relative mass. That m2 being the smaller mass should have a greater change in velocity. Well, the velocity of m2, let me start over again. Because m1 has a smaller mass, it should experience a greater change in velocity. So m1 starts with a velocity of v and ends with a velocity of negative 2v. That's a change in velocity of negative 3v. So that's negative 3 velocities, or however you want to talk about it. m2 starts with a velocity of v and ends with a velocity of 2v. Now that's only a change of positive v. So the first mass changes by a velocity of negative 3v. Second mass changes by a velocity of 1v. And so their change in velocity is related to their relative masses. Anyway, the other problem is much more involved with multiple concepts, and I want to do this in these videos because I don't want to leave behind all of the concepts that have come before. So a ball is released from the top of a hill that's 3 meters tall, rolls to the bottom, and collides with a cart of equal mass. The ball sticks to the glue on the back of the cart. With what speed do they move after the collision? So this is the initial position of the cart, and then once they have collided the cart is now moving with a ball stuck to the back at a new velocity. So when you think about what physics concepts to use, any collision is always going to be a conservation momentum situation. Sometimes it doesn't lend itself to that, but usually it does. Any hill, you can do a combination of kinematics and forces, or you can do energy. And so this one really lends itself to energy. The way it's drawn is literally pushing you toward using energy, because that hill is not a ramp. If it's a ramp, then you might want to think about using forces and kinematics. So we're going to do energy first. The idea here is the mechanical energy of the ball Earth system is going to be constant all the way down until it collides with the cart. So we're going to use conservation of energy to figure out how fast the ball is going when it hits the cart. Once we know that, we're then going to apply conservation of momentum to figure out how fast the two of them are moving after their collision. So for the ball, we start with gravitational potential energy because the ball is above the lowest point here, and we end with kinetic. And we can cancel mass because it's both the same and in both terms. And so then we can plug in our values. So 10 times 3 equals 1/2 v squared. So if I manipulate that, I get that the velocity of the ball is 7.75 meters per second. So when the ball gets to the bottom of the hill, it's moving at 7.75 meters per second. Now I can use the momentum concept to figure out how fast they go after they collide. Now this is something where they're going to stick together, so I can do mass of the ball times the initial velocity of the ball plus the mass of the cart times the initial velocity of the cart, and then they stick together. So the mass of the ball, I'm going to move that over, mass of the ball plus the mass of the cart times that final velocity. They are in fact equal masses, and so I can just replace all those masses with m. The other thing I want to do is I want to get rid of the initial momentum of the cart, because the cart is at rest. The cart is not going to be moving and has no momentum before that collision. So I can replace all this with m times 7.75. That's the initial velocity of the ball. And then I have two masses that are equal, so I'm going to put that as m plus m. And that's going to be times final velocity. Awesome. I love notifications. Okay. Last but not least here, 7.75 m equals 2m times Vf. So now I have consolidated. I have m on both sides, and I just want to divide 7.75 by 2. And so that's going to be a final velocity of about 3.87 meters per second. I picked simple masses, and you'll notice maybe that this final velocity is exactly half the initial velocity, because when two identical objects collide and stick together, you can think of it as the mass of the system doubles, so the velocity will get cut in half. As I said, there's many more looks at conservation of momentum, but this will get you started thinking about what type of interaction it is. This was an explosion, this was an inelastic collision, and then moving on from there.